In this next video, we're going to look at asymptotes. And for our definition of an asymptote, we're going to say if we have an f of x such that the limit as x goes to infinity of f of x is equal to L, or the limit as x goes to negative infinity of f of x equals L, then f of x has a horizontal asymptote at L. Now, for most of the asymptotes we looked at before, you're looking at vertical asymptotes. And we've kind of already talked about those. Those, again, are if we're looking at right or left-hand limits going to a particular value, and the value of the limit goes to infinity. Here, we're actually looking at what we consider the end behavior of a function. So as our x's get bigger or smaller, what happens to the value of the function in the long run? Okay. More formally, if f of x is defined on the interval from negative infinity to a, then the limit as x goes to negative infinity of f of x is equal to L, means that for all epsilon greater than 0, there is an n such that x is less than n and f of x is minus L. The distance between those is less than epsilon. And so here this again is kind of like our precise definition of the limit, and we can look at it from the other side. So thinking the interval from a to infinity, and the limit as x goes to positive infinity. And so there we would change x being greater than n instead of less than n. Okay, so let's look at an example. Let's say we have the limit as x goes to infinity of 2x squared plus 1 quantity squared over x minus 1 quantity squared times x squared plus x quantity. Okay? And we want to find the limit of this, like we said, as x goes to infinity. Well, if we look at our properties that we've talked about with the analytic method, there's not really a way to just plug in, because infinity isn't just a number. It's kind of a collection of numbers as they get bigger and bigger. So here, what we can do is we can think about what happens to the terms as x gets bigger. Okay? So again, using the analytic method, what I'm going to do is I'm going to rewrite the function. So we're going to look at the limit as x goes to infinity, and I'm going to divide out by the highest powered term. And what that's going to do is I'm going to reduce my fraction to smaller terms so that I can look at what each of those terms does as x goes to infinity. Because right now I've basically got something really big squared over something really big, and I really can't tell at that point what's happening. So let's divide out by the highest powered term. So ignoring the extra exponents on the outside, let's divide everything by an x squared. But let's go ahead and FOIL out first. So we're going to get a 4x to the fourth plus 4x squared plus 1 over x squared minus a 2x plus 1 times an x squared plus x. And then we can see that x to the fourth is our highest powered term. So I'm going to basically take and multiply top and bottom by x to the fourth, 1 over x to the fourth. Okay, again, all that's going to do is divide that out of those terms. Okay? So on the top, I'm just going to do that. Dividing out by x to the fourth looks like a 4 plus a 4 over x squared plus a 1 over x to the fourth. On the bottom, I want to do this a little differently. So I'm going to take that x to the fourth and I'm going to split it into an x squared and x squared. And I'm going to divide the first term by an x squared. And I'm going to divide that second quantity by x squared. And again, I could have just multiplied it out and got a fourth degree polynomial and then divided everything by x to the fourth. But this just saves me a little bit of work of having to multiply that out. But now I can use my properties, right? Our limit laws say that if I've got sums and differences and products, I can look at what's happening as x goes to infinity. And here I have a better idea of what's happening to each of the terms Whereas the original, again, we had quantities to powers, and something like infinity squared doesn't really mean much other than it's a really big number. So now looking at each term as x goes to infinity, well, we've got our constant term. 4 over x squared as x goes to infinity is just 0. And likewise, 1 over x to the 4th as x goes to infinity is also 0. Looking at the denominator, we'll get a 1 minus 0 plus 0. That quantity times 1 plus 0. And so here we can see this is basically going to be a 4 over a 1 times 1, or our limit is going to go to 4. In this next example, the limit as x goes to infinity of e to the negative x plus 2 cosine of 3x. So again, the idea is the same. We want to find what happens as our x's get really big. So again, in this case, we'll use our limit laws. And we'll start by separating out the limit. So here we can look at the limit as x goes to infinity of e to the negative x plus the limit as x goes to infinity of 2 cosine 3x. And so in the first piece, we can see very easily what this is doing. If you have to rewrite that function just to understand what's happening there, you can do so. So this, again, is just 1 over e to the x. And so here, again, we can see as x gets very large, our function value gets very small. So this is going to go to 0. For this other term, we have to be a little careful. And the reason we have to be careful here is because cosine of 3x is a periodic function. So as I move along the x-axis, it is always bouncing between positive and negative 1. And depending on where I stop, meaning as I go further and further out, my values could be positive or they could be negative. But because there's no way to tell at a particular point in the distance whether this is a particular number, this piece of the function is undefined. Or, again, we can think of it as the limit does not exist. So here, when we're looking at this limit, the limit as x goes to infinity of e to the negative x plus 2 cosine of 3x, we would say this limit does not exist. And again, that's because the cosine piece is bouncing between two numbers as we move further out, and it's not headed or approaching one single value. So in this last example, we're going to use our analytic methods to evaluate the limit again. So here we're given the limit as x goes to negative infinity of the square root of 1 plus 4x to the 6th over 2 minus x cubed. And so again, because I'm looking at something rational, I'm going to start by trying to simplify both the numerator and the denominator by dividing out by a common term. And so in this case, if we look, x to the 6th looks like our highest power, but again, that's inside of a square root. So really our x to the 3rd is our highest power. So we'll take a 1 over x cubed divided by a 1 over x cubed and multiply that through our expression. So we'll get the limit as x goes to negative infinity of the square root 1 over x cubed. Okay, and notice here, 1 over x to the 6th. Notice here I'm dividing by a 1 over x cubed, but when I put it back into the square root, it's actually an x to the 6th. So here we'll get 4. And then on the bottom I can divide out, so we'll get a 2 over x cubed. But here you got to be a little careful. It looks like x cubed over x cubed should just go to 1. But because I'm actually looking at negative infinity, when I look at those values, it's actually going to go to positive 1. Okay? Because all of my numbers are negative, and when I look at negative x cubed going to negative infinity, that's actually going to positive values. Okay? And so here, simplifying my expression by taking the limit, 1 over x to the 6 is going to go to 0. 4 is a constant, so it's just going to go to 4. On the bottom, 2 over x cubed, again x cubed will go to negative infinity, but 2 divided by that is still going to go to something like 0. And then for that last term, again we have a constant, so that's just going to be 1. Okay? So from there we can evaluate. We can see the top square root of 4 is just going to be 2. On the bottom we get a value of 1. So there's our limit. And again, all this limit is telling us is that we have a horizontal asymptote at y equal 2.